But if some capacities are not rational, then this algorithm may not give us the maximum flow. Not only that, more surprisingly, the values of the flows in this sequence may not even converge to the maximum value of the flow. So let's consider an example. So consider this network. Here we have many edges with capacity very large. Let me just write the infinite sign because it doesn't really matter how large this number is. So let's say this infinite are all okay. Assume this is like 1 million. So all the infinite sign have the capacity 1 million. And then these three edges have the, small capacity 1, alpha square, alpha. Here alpha is actually, let me write it here. Alpha is a number satisfying certain, property. Alpha cube plus alpha minus 1 equals 0, and alpha is positive. So this is a polynomial with degree 3, and it has a unique positive root. And then let it be alpha. Alpha is actually, number which is smaller than 1 and bigger than half, I think. And here we want to show that if we apply this Ford-Fulkerson algorithm, then we might not be able to get the maximum flow. Moreover, our value might not even converge to the correct value. Here, the correct value is, say, very large number, depending on what number we put in on this infinite. But if we put 1 million for all this number, then maximum flow, the value should be more than 1 million. So what we can do is we have to take the So now assume we do the Ford-Fulkerson algorithm. And then we first take this augmenting path. This is an augmenting path. At first we have the zero flow. In zero flow, this is an augmenting path. And if we augment it, then what happens? Then this becomes 1. This has value 1. And this has value 1. And this has value 1. And then we augment along this path. So this is again a F augmenting path. So we augment it, then this edge now has a value alpha, and this has alpha, this has alpha. Because alpha is the smallest, positive number on here, so we can increase by at most alpha. So this is alpha, alpha, alpha. And then we take this augmenting path. Then this has the smallest capacity, so we can increase by alpha square plus alpha square alpha square, alpha square. So from now on, we can keep to the augmentation, and let's consider these 4 edges only. Note that all the other edges have large capacity, and then on the augmentation they will keep increase. So really we have to look at these numbers. So this is 0, this is 1, alpha square, alpha, with this, 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 this. More generally, let's say this is alpha to the 4m with m1. This is alpha to the 4m plus 1. This is alpha to the 4m plus 2. Here m is 0. Now first, what we want to do? We want to take the augmented overlapping path, which is S, C, D, A, B, T. So this is an augmenting path. Here this has infinite capacity and this is infinite capacity. It doesn't really matter if this has infinite capacity. And we only have to consider these two. And alpha is smaller than 1. So for this P, epsilon P is alpha. More generally, when m is 0, it's alpha to the 4m plus 1. So this m is a counter. We will keep augmenting it by first time, second time, third time, fourth time, and then we will repeat it. We will keep repeat augmentation, and then this, repeats up to modular 4. So now that's why we introduce this m. So what we do is, along this, let me delete these red things. I have written too much, so let me just delete it. So along this, we augment by epsilon p equal alpha to the 4m plus 1. So then what happened? So this, after augmentation, this decreased by this much, and this decreased by this much, and this increased by alpha to the 4m plus 1. And yeah, that's it. Then what does this become? So first, this becomes 0. And this becomes alpha to the 4m plus 1. And this stays same. And this becomes alpha to the 4m times 1 minus alpha. And 1 minus alpha is same as alpha to the 3. So this becomes alpha to the 4m plus 3. So that's what we have done. Augment by SCDABT. So this is new flow. And then on here, I mean, of course, the value on this edge and this edge has increased, but let's not keep track of it because it's not so important. Because its capacity is infinite, so we can keep increase whenever we want. And we augment now by SCBADT. So SCBADT. So again, here we only have to see this three number. So this can be decreased by at most this much, and this can be decreased by at most this much, and this can be increased by at most the capacity alpha. Out of that smallest one is this alpha to the 4m plus 2. So in this case, epsilon p is alpha to the 4m plus 2. So previous case was alpha to the 4m plus 1. Wait, sorry. Let me delete that red line. So then what happened? You subtract that amount and you add that amount from this BA, and then here you subtract that amount. Then how does it change? So this becomes alpha to the 4m plus 2. And this becomes 0. And what does this become? That's same as alpha to the 4m plus 1, 1 minus alpha, which is, this is same as alpha to the 3. So this is simply alpha to the 4m plus 4. And then now we want to augment it again by SABCDT. So SABCDT. So this is again on augmenting path. So we don't have to check this too because its capacity is infinite, so we can augment as much as we want. But here, so this can be decreased by this alpha to the 4m plus 2 amount, and this can be increased by 0 to its capacity, alpha to the 2. And this can be decreased by alpha to the 4m plus 3. And this is the smallest value. So we have to augment it by this much. And then again, this will decrease by the same amount, and this will be increased by this amount, and this will become 0 by decreasing by that amount. Again, by the same computation, this is same as alpha to the 4m plus 5. And then lastly, we can augment again by SADCBT. SADCBT. C, B, T. Again, these two edges have infinite capacity, large capacity, so we don't have to worry about. So it will traverse in this manner. Again, this can be decreased by alpha to the 4m plus 4, and this can be increased by at most its capacity 1, which is larger than other value, and this can be decreased by alpha to the 4m plus 3, which is bigger than alpha to the 4m plus 4. So we can augment it by alpha to the 4m plus 4. So once you do that, this becomes 0. You subtract it, and you add 4m plus 4, and you subtract alpha to the 4m plus 4. Then this again becomes alpha to the 4m plus 6. Then this is same as 4 times m plus 1. This is alpha to the 4 times m plus 1 plus 1. This is 4 times m plus 1 plus 2. So, from the previous situation, everything is same, but the m is replaced by m plus 1. So with larger value, we can keep repeat this. We do this, and then we come back and we do this, and we do this. We keep repeat this. Then by keep repeating it, we can, keep finding this augmenting path. So we never get stuck. And then while you're doing that, what's the value of this flow? So initially we add this 1. So sorry, I didn't write that. This was actually 1 plus alpha square. So this 1 plus alpha square, and this is alpha. So initially the flow value was 1 plus alpha square. But after that, we keep add alpha to the k, where k is 1, 2, and so on. And how large is this? Because alpha is smaller than 1, this actually converges. With simple calculation, we can actually show that this is, smaller than, say, 6. So we have this network with some capacity irrational. And then we apply this Ford-Fulkerson algorithm. Then this algorithm never terminates. And then the values that this algorithm gives converges to some number smaller than 6. However, this original network has very large maximum flow. Let's just take these two, and then we assign 1 million, 1 million, then we get a flow with 2 million. So again, this infinite is not really infinite. This is just some large number. Anyway, so this shows that this Ford-Fulkerson algorithm may not work for the, general case when capacities of the network are not rational. But what's the problem here? Why it didn't work? The problem is we have taken long passes, long augmenting passes. So when a network is given, there may be more than one augmenting path. Then you have to make the decision whether to go with this augmenting path or the other augmenting path. But in the above example, we made the wrong choice. So we can actually improve this algorithm by giving instruction to choose the right augmenting path.